Hi, Hola, Bonjour, Privet, Salaam. Welcome to Blueprint Bazaar. We're glad to have you here as we dive into another exciting engineering creation, showcasing the intricate design and robust functionality of a key component in our shredder machine, the shaft. This description will take you through a deep exploration of the SolidWorks modeled shaft, highlighting its structural integrity, detailed features, material selection, functional requirements, and role within the overall shredder assembly. The shaft, although often considered a standard component in mechanical assemblies, is the heart of rotational movement, and in a shredder machine, it bears a significant amount of mechanical stress, torque, and dynamic load conditions. Therefore, the design of the shaft is approached with a blend of precision engineering, simulation validation, and manufacturability considerations, ensuring that every detail supports high performance, safety, and durability. The shaft in question was modeled entirely in SolidWorks, a powerful CAD software that offers parametric design, simulation integration, and real-time visualization of mechanical components. Using the software's part environment, we began by creating a central cylindrical body as the core of the shaft, defining its length, diameter, and concentric features with respect to the machine's dimensional constraints. The shaft serves as the main driving element of the shredder blades and must accommodate a series of mounted components such as bearings, spacers, keys, locking rings, and of course, the shredding cutters. Therefore, the initial geometry had to allow for these attachments while maintaining balance, precision, and ease of assembly. In SolidWorks, we utilized reference planes and center lines extensively to ensure perfect alignment and symmetry throughout the shaft design. We applied various features, such as extruded boss base, for creating solid cylindrical sections, and revolve features to model fillies and tapered ends. The key slots were carefully crafted using the cut extrude feature along with precise dimensioning tools to ensure that the shaft could accept standard key sizes for power transmission components. Fillets and chamfers were not merely aesthetic choices but functional necessities to prevent stress, concentration at edges, a critical consideration for a component that will endure cyclic torsional loads during operation. To ensure the shaft would be structurally capable of withstanding these forces, we conducted a series of simulations using SolidWorks simulation tools. These simulations evaluated the stress distribution, deformation under torsional load, and safety factors based on different material selections. Ultimately, we selected a high-carbon alloy steel, specifically AISI 4140, known for its excellent strength, wear resistance, and machinability. This material is commonly used in heavy-duty shaft applications due to its toughness and ability to withstand fatigue. The yield strength and hardness of AISI 4140 ensure that the shaft won't warp or fracture under load, even during prolonged operational cycles. The shaft includes multiple stepped diameters, allowing for the accurate positioning of bearings and spacers along its length. Each step was carefully dimensioned to fit standard bearing bores and facilitate easy installation and maintenance. The shaft ends are designed with threaded regions to accommodate locking nuts and retainers, securing the assembly tightly within the shredder housing. These threads were modeled precisely using the cosmetic thread tool for appearance and documentation purposes, although actual thread profiles were also optionally created for simulation analysis. Additionally, grooves were added for circlips or retaining rings, which are essential in preventing axial movement of the mounted components during machine operation. Keyways were modeled along the shaft length to engage with the cutters and locking discs that form the core shredding mechanism. These keyways were designed according to isometric standards, using SolidWorks reference geometry and cut-extrude functionality. The depth and width of each keyway were calculated to optimize torque transmission while avoiding overcutting that might weaken the shaft. Each keyway was placed using the sketch dimension tool, ensuring alignment with the blades and spacers in the shredder's exploded view assembly. We ensured that all rotational components were symmetrically distributed to maintain rotational balance, which is crucial in high-speed rotating machinery to avoid vibration and wear. One of the most useful features in SolidWorks that we utilized was the mate functionality during the shaft's integration into the shredder assembly. By mating the shaft with bearings, housing supports, and cutting discs, we were able to simulate the rotational movement and verify that there was no interference or misalignment. This helped validate not only the shaft design, but also its relationship with other parts in the assembly. The dynamic simulation tools allowed us to animate the rotation of the shaft and visualize the engagement between the cutters and stationary components, providing valuable insights before physical prototyping. We also took care to model the shaft with machining tolerances in mind. Using SolidWorks dimensioning tools, we specified tolerance values that would allow the shaft to be manufactured with conventional turning and grinding processes. Fit types were designated according to the intended application. For example, interference fits for bearing press fits and clearance fits for components requiring easy removal. The detailed drawings derived from the SolidWorks model include all necessary annotations for manufacturing, such as GD and T geometric dimensioning and tolerancing, surface finish symbols, and notes for heat treatment requirements. Another critical aspect of the shaft design was its support structure. In the shredder machine, the shaft is supported by pillow block bearings mounted on either side of the frame. Therefore, the shaft ends were designed to be compatible with these bearings, with proper seating regions and chamfered edges to aid in assembly. SolidWorks' ability to simulate exploded views was invaluable for visualizing the shaft's interaction with the machine's frame and for preparing assembly instructions. Weight optimization was another factor taken into account. A heavier shaft increases inertia and power consumption, whereas a lighter shaft may compromise structural integrity. Through SolidWorks mass properties analysis, we were able to calculate the shaft's weight, center of mass, and moments of inertia, allowing us to tweak the dimensions for an optimal balance between strength and weight. In fact, the final version of the shaft was 8% lighter than our initial concept without sacrificing any functional properties, thanks to strategic design refinements. We also leveraged SolidWorks' material library to assign accurate visual and physical properties to the shaft. Applying realistic appearances, such as machined steel or black oxide coating, helped us prepare photorealistic renders of the shaft using SolidWorks Visualize. These renders are especially helpful for presenting the design in client meetings or marketing materials. By animating the shaft's rotation within the full assembly, we created an engaging and educational visual experience for our Blueprint Bazaar followers, showcasing the level of engineering detail that goes into even a single component of our machines. Throughout the design process, attention was paid to manufacturability, serviceability, and long-term durability. Features were incorporated to make the shaft easy to remove, inspect, and replace if needed. The design supports lubrication systems and integrates alignment marks to assist technicians during assembly. These considerations are often overlooked in theoretical models, but are critical in real-world usage. especially in heavy-duty machines like shredders that operate in demanding industrial environments. The shaft was engineered to function as the primary rotating axis that supports and drives the shredding blades with consistent torque and alignment. Using SolidWorks, the design process began with defining the exact dimensions necessary for fitting within the shredder assembly, considering factors such as bearing placement, blade spacing, and the housing's spatial limits. The model included multiple diameter transitions to accommodate different mechanical elements, including snug fits for bearings and keyed regions for torque transmission. To achieve efficient power transmission, keyways were added at calculated intervals along the shaft. These keyways were dimensioned according to international standards to guarantee compatibility with standard machine keys and corresponding key slots in the cutting discs. The position and length of each keyway were determined by the torque requirements of the individual shredder blades, ensuring that the applied forces would be evenly distributed throughout the shaft. SolidWorks' cut-extrude feature allowed precise placement of each keyway, and mating simulations helped verify alignment with the surrounding components in the full assembly. In addition to mechanical functionality, durability and ease of maintenance were central to the design approach. The shaft material was selected from SolidWorks' material library with performance in mind, ultimately settling on a hardened alloy steel known for its fatigue resistance and machinability. Stress analysis simulations were run using SolidWorks simulation to evaluate the effects of torsion and bending loads, helping to identify weak points and validate the final geometry. Fillets were applied at key intersections to reduce stress concentration, and surface finish annotations were added to guide manufacturing standards. For improved operational reliability, grooves were incorporated into the shaft design to house circlips or snap rings, effectively limiting axial movement of the mounted components. These grooves were dimensioned to fit standard retaining rings and placed precisely using reference geometry to correspond with the position of spacers and bearings. Additionally, to enhance serviceability, alignment marks were included along the shaft's outer surface, enabling technicians to assemble or disassemble the system without guesswork. All these features were validated in the context of the full shredder assembly using motion studies and exploded view analysis, ensuring that each part worked harmoniously under dynamic conditions. In conclusion, the shaft designed in SolidWorks for our shredder machine is a testament to how digital engineering tools can be used to create complex, highly functional mechanical components. It combines mechanical design principles with digital simulation and visualization to ensure optimal performance and reliability. At Blueprint Bazaar, we aim to bring such mechanical marvels to life, with every nut, bolt, and shaft serving a purpose in the greater engineering story. We hope this detailed walkthrough of the shaft design has given you a greater appreciation for the level of craftsmanship and thought that goes into every part we make. Stay tuned for more engineering insights and full assemblies as we continue to innovate, design, and build at Blueprint Bazaar.